Okay, let's start from the beginning. Hello everyone, and hello Aditya for joining me at this time. I am Dr. Sutanu Bhattacharya, and your new instructor who will taken care of. I will take care of this course, discrete structures, from now onwards. And if you have any questions regarding your previous assignments or previous grading, please reach out to the previous instructor, Ms. Donna Jackson. And from now onwards, whatever assignments I'll release, I'll take care of everything, including your final exam. And today we'll start from a new topic, and which is very interesting and which has very vast application in computer science. So that topic is a graph. I think you can share my, you can see my screen, hopefully. Okay. Can you see my screen?
Yes, sir, it is visible.
Okay, that's great. So the topic is graph. We'll start a brand new topic so that if you have any shortcomings in understanding any previous topics, that should not be a bottleneck to understand this topic. I'll make sure that. And feel free to reach out to me if you have any concern, if you have any doubt, and I will help you and I'll work with you. And as I mentioned in my previous announcement, last day's announcement, you are free to reach out to me during my office hours, which is Tuesday, Wednesday, and Thursday from 12 to 2 p.m. And you are welcome to stop by at 309L Goodwin Hall, which is my office, and or you may send me an email to make an appointment through over Zoom so that we can meet over Zoom. I'm okay with that. And obviously provide me feedback, whatever you feel, whatever you suggest me to do that, so that I can improve my teaching, or whether it will help you to understand the new topics. Feel free to provide those feedbacks. I will change my teaching styles according to that. My goal is your success. So I want to make sure that you succeed after taking this course. Although we don't have enough time, only around 1 month. So just I will work with you to make you succeed. So whatever you need from me to make you succeed, just feel free to let me know. I will work with you to get that. Okay, let's start with the new topic, graph. And let's assume John is a friend of Aditya. Aditya is a friend of Aaron, and maybe Aaron is also a friend of Peter. And also maybe Aditya is also a friend of Peter. And maybe John is also a friend of Peter. So it's a friendship graph where there are 4 persons: John, Aditya, Aaron, Peter, and this connection is saying that who is a friend of whom, the friendship relationship. So we can see there are 2 components here. One is the person, and if there exists any relation between those 2 persons. So here I have represented the friendship using a graph. So the person is denoted like this circle is called vertex, or in plural it is vertices. We often mention it as nodes. So all are same, vertex, vertices, or nodes. I interchangeably might use nodes sometimes. So just when I mention nodes means I am mentioning vertices. So here vertices are John, Aditya, Aaron, Peter, all those vertices. And the relation between 2 persons we'll call age or edges. So this is one edge which illustrates the relation between John and Aditya. At the same time, there is no edge between John and Aaron. So that means John is not a friend of Aaron. Don't take it seriously. I'm just taking an example. So you are all friend maybe. So I'm taking this example. So this is a graph where there are some persons or nodes or vertices are there, and there is a relation between those persons. So we'll represent a graph. We will represent a graph as follows. G equals to V, comma, E. Now I know you don't you have not studied set yet. Maybe you have some concept in your school days mathematics course that you took in your class 11 or class 12. So what is set? Set is a, you may think, collection or bag. In your bag, you have books, you have water bottle, you have maybe umbrella, pens. So it's some collection. Set is some collection. Now, collection of same kind of data, collection of similar kind of data. So G is a graph which contains set V and set E. I will cover set later on, but I will provide enough details about set so that you don't feel any obstacle to understand this concept. So here V is a set. V is a set of vertices, and E is a set of edges. So nothing but it's a collection of edges and it is a collection of vertices. So for this example, friendship example, what we have taken, V is nothing but is a collection of vertices, that is John, Aditya. So V contains John, Aditya, Aaron, and Peter. So this is set V. This is set V, and the order doesn't matter. You can put Peter before John, the order doesn't matter. So this is set V. And what is edges? So edges is a relation. So one edge we got from John and Aditya. So we can present it like this, John, comma, Aditya. I'm not writing the whole name to save some space. Another edge is Aditya and Aaron. So Aditya and Aaron. Another edge is Aaron and Peter. Another is Aditya and Peter. And another is John and Peter. So this is the set edge. Up to this point, although only 2 students are here, so do you have any questions, or is it clear to you so far?
Yes, sir, it is clear.
Okay, great. It's very easy actually. So graph is nothing but a collection of vertices or nodes and collection of edges. That's all. So you need to know this basic thing. So graph is this collection of vertices and collection of edges, and we will represent any graph using these 2 terms, vertices and edges. Now, graph can be, this is one example of graph where this edge is saying that John is a friend of Aditya. At the same time, Aditya is a friend of John. Okay. Now, it may happen that John knows maybe some celebrity, maybe who is one celebrity, maybe Mr. President, or James Bond. Here it is saying that I am directing. Previously, the edge was undirected. But here I am representing that John knows James Bond. But it is not necessarily that James Bond knows John, because James Bond is a celebrity. So we all know James Bond. So here edge is directed. So graph can be distinguished between one is undirected graph, another one is directed graph. Undirected graph means the edge should not have any direction. So in this previous example, this edge doesn't have any direction, means it has both direction, you can think. So John is a friend of Aditya, Aditya is also a friend of John. Same, John is a friend of Peter, Peter is also a friend of John. But in case of directed edge, like John knows James Bond, but James Bond might not know John, or might be. If James Bond knows John, then there is another directed edge from James Bond to John. So we can distinguish graph based on undirected graph and directed graph. So we can take another example of undirected graph. We can represent this like this way. This is an example of undirected graph. So no direction is associated with edges. An example of directed graph can be like this. Maybe something like this. So this is undirected graph and directed graph. And this edge can be represented like V1, V2. This is V2, V3. And this is V1, V3. Now the order matters in case of directed graph. V1, V3 is not same as V3, V1, because the edge is directed from V3 to V1. Sorry, this is this would be V3, V1. So V3, V1. So the directed edge is from V3 to V1 is not same as V1, V3, because this edge is not present in this graph. But in this case, the order doesn't matter, V1, V3, because both it's an undirected edge. So V1, V3 is same as V3, V1 in case of undirected graph. That's very basic thing. I hope you have understood it. Now, okay. Next, we'll talk about simple graph. But before talking about simple graph, let me clear you one thing, that first of all, why graph is important. Just think you are currently at Montgomery and you want to go to maybe Atlanta, and what you will do? First, you will do Google Map. You will search Google Map to find a shortest path or efficient path. But there are many paths which leads to Atlanta. Now you need to find the shortest path to reach to Atlanta. This is actually a graph problem. So Montgomery is one vertex, Atlanta is another vertex, and in between there might be Auburn is there, maybe Columbus is there, many intermediate nodes are there. So you need to find shortest path from source to destination. This is one major application of graph. At the same time, if you have taken networking course, so right now, this is one great example. Right now we are doing Zoom session. So whatever I'm teaching right now, you can watch. How? So this is my computer, which is source, and this is your computer. Maybe it is destination. Intermediate, there are multiple routers are there, multiple routers, which helps to send this packet, this online session, this packet from the source to up to towards your laptop. But how? This is also a finding shortest path, finding efficient path, finding a good path. So this is another application of graph. At the same time, I believe you all have a Facebook account or maybe Twitter account. So this is nothing but a friendship graph that we drawn before. This is your profile. This is your friend's profile. If that person is in your friend circle, then there is an age. If the person is not your friend, so there should not be any age. So it's a complicated graph. So just think, if in case of Facebook, there are billions of user profile. That means number of vertices or number of nodes is billion, and ages represent whether that person is in your friend circle or not. So it's a complicated graph. So online platform like Facebook, Twitter, LinkedIn, all actually are using graph problem. So that's why graph is so important. And whatever we'll cover right now, that would be helpful for you when you will take data structure course, when you take algorithm course, when you will take networking course. That's why graph is so important, and that's why I have chosen graph for the first as a first topic to discuss. So I hope you have got the background of the importance of this topic, graph. Okay, so let's talk about simple graph. So simple graph means no self loop and at most one edge between any two nodes. So first, let's try to understand what does that mean. This is actually a short form of between. So I'll use shorthand. So this is one example, P1, P2. Now self loop means like this. You may think in case of friendship, you may think that I am also my own friend, right? So this way there is a self loop. That means V2 is a friend of himself. So V2 is a friend of V2. So I am also a friend of myself. So that thing. So simple graph doesn't contain any self loop. So this self loop should not be there in case of simple graph. At the same time, at most one edge, at most maximum one edge between any two nodes. So what are the two nodes? Any two nodes. V1 is one node, V2 is another node. There is only one edge, not more than one edge. Maximum one edge. There might be no edge at all. Like it is also a simple graph like this way. Suppose there is no edge between V2 and V3, and also there is no self loop. So in this case, this is also a simple graph. V3 to V2, there is no edge. That's also perfectly fine. But this is not a simple graph. So here multiple edges are there. So whatever problem we'll discuss from now onwards to when you take networking algorithm, so whatever problem you will discuss, all are based on simple graph. Means no self loop, no multiple edges between two nodes or two vertices, only single edges. So if we make it simple, so this is an example of simple graph. But in case of undirected, can you say that this is a simple graph or not? Can you say anything? Is it a simple graph?
I have a question.
Yes.
In the first graph between V1 and V3, there are two directions, like two edges. So I think that is not a simple graph.
Good question. But yeah, great question, Aditya. The difference between, try to understand the difference between these two graphs. One is undirected, one is directed. Now, this is a directed graph, means that's V1, V3. Like, you may think this is one-way road. So when you take I-85 to reach from Montgomery to Atlanta, you might be taking I-85 south. And when you are returning back, you are taking I-85 north. So the road is not same, right? This is directed edge. But in case of undirected edge, for this example, this is not a valid simple graph because both edges are same. So this is not a simple graph, but this is a simple graph because this directed edge is from V3 to V1, which is not same as V1 to V3. Is it clear to you?
Okay, so similar edges should not be there, basically.
Yeah, same edge. Same edge should not be there. Only one edge should be there. But when there is a direction associated with any edge, this edge and this edge are not same. They are different. Okay?
Okay, got it. Thank you.
Yeah. So this is about simple graph. So whatever problem we'll discuss from now onwards would be simple graph. So no self loops, no multiple edges. Very simple. Make it very simple. Don't make it complicated.
I have a question.
Yes. Yeah.
So it's multiple edges. Are you basically creating a self loop here with V1 and V3? Since there's no direction, it's basically they both have their own self loops.
You are right. That's why it is trying to avoid that multiple edges.
Gotcha.
Yeah, but that doesn't. You don't. It's a cycle. I would not say it's a self loop because in some cases, let me draw another one like this way. See, there exists a cycle, right? But it is a simple graph. Right?
Yes.
Yeah. So this type of cycle is applicable in case of simple graph, because it is saying that V1 is a friend of V2, V2 is a friend of V3, and V3 is a friend of V1. That's perfectly fine in our case. So that is simple graph. So simple graph is very simple, no self loop, and at maximum one edge would be there between two nodes. That's all. Very simple. Now we'll talk about degree. It is important. Degree of a vertex. It is nothing but a number of friends. That's the degree. So in this example, the previous example, the first example, John has two friends, Aditya and Peter. That means the degree of John would be 2. Aditya has 3 friends, John, Peter, and Aaron. So the degree of Aditya is 3. Aaron degree is 2 because it has 2 friends. Peter has 3 friends. So degree is nothing but, you may think for this example, number of friends, but it is very important. And in case of undirected graph, let's take one example is R, C, D. So degree of S would be 1 and 2. So 2 edges are incident on S, so the degree is 2. Degree of R would be 3 because 3 edges are incident on R. That means R has 3 friends. You may think like this way. Degree of C is 2. Degree of D is 3. So this is degree of a node. That is, so degree of a node is nothing but a number of edges incident with a node. That is degree. And obviously this is for undirected graph. This is the degree. Directed graph, it would be, one would be in degree. So this is a node. Suppose the node looks like this way. So this edge is incident with this node. So this is, so each node will have in degree and out degree. So when you calculate in degree, then you need to calculate how many edges are incident on this, on a particular node. And when you calculate out degree, you need to calculate how many edges are going out, going outside direction. So that will calculate out degree. But overall degree is that number of edges connecting to, connected with a node. That is degree. So let's do a couple of examples to grasp this concept. So this is one graph. So this dot is represented as a vertex or vertices or nodes. So same thing, you may draw like this way or draw like this way. So this is one vertex, B, then okay, B, C, D, E, F. Now let's calculate degree of every node. So what would be the degree of A?
1.
1, right? Very easy. What would be the degree of B?
3.
3, right? Because 3 edges incident with B. What would be the degree of C?
4.
4, right? D would be 2, E would be 1, 2, 3, and degree of F would be 1, 2, 3. Great. Do another one. And okay, this is fine. Now, one very important, you may expect this question in your final exam, the relation between degrees and number of edges. For any simple graph, can you find any relation between degrees, summation of degrees, not degrees, total degrees of all vertices and number of edges in that graph? Is there any relation? So just go through this example. In this graph, this is a graph. It contains 1, 2, 3, 4, 5, 6 vertices and multiple edges. AB is one edge, BC one edge, CD, like this way, multiple edges are there. So first tell me number of edges in this graph. How many edges are there in this graph?
8.
Okay, let's see. 1, 2, 3, 4, 5, 6, 7, 8. Right. And what is the summation of degrees? Means degree summation of degrees of all edges,
60.
all vertices. So 1 plus 3 plus 4 plus 2 plus 3 plus 3. It is 16, right?
Yes.
So can you get any relation?
Yeah, the degrees is twice as that of edges.
It seems like that, right? So here it seems that summation of degrees equals to 2 multiplied by number of edges. We can use number of edges like this. So it is number of edges. So it seems that this is some relation. You can take any other graph, you will see the same relation. Now, obvious question would be, is it general? Means, is it true for all simple graph? If so, how to prove that? Can you prove that? So can you prove that summation of degrees equals to 2 multiplied by number of edges? Can you prove that? Or is it always true? So is it always true? This is very important to know for your final exam as well as to grasp the concept. So what do you think, Aditya or William?
I don't think it is always true.
Really? Okay, let's see.
Okay.
Let's see whether it's always true or not. So let's take this one edge, AB. Okay. So let's take one edge, A and B. This is that edge I have taken. Okay. So this one edge, what is the contribution of a single edge to the degree of a node? This single edge AB contributes 1 degree for A and another 1 degree for B. Do you agree?
Yes.
So this one edge, because of this edge, you have mentioned that degree of A is 1, right?
Yes.
And because of this edge, you have also counted degree 1 for this particular edge for this vertex B.
Yes.
So when you calculated degree of B, how you get 3? Because you consider this edge, and this edge. So you consider this edge to calculate degree of B. You also consider the same edge to calculate degree of A. So every edge contributes 2 in degree. In case of A, and 1 and another 1 in case of B. Are you getting?
Yes, sir. I got it.
Okay. Another easy example would be I really feel bad because we don't have offline class. Otherwise, it would be better to explain. So suppose this is my hand. Okay, I'm very good in drawing, and maybe this is Aditya's hand, and we are doing handshaking. Okay, so we are handshaking. So we are handshaking. To make a to handshake, how many people do you need?
2 people.
2 people. This is 1 people, this is another people. So you may consider this handshaking is making an edge, and to make this edge you need 2 people, or one handshake contributes 1 to this person, another 1 to this person. So same thing, this is handshaking between 2 vertices. So this one edge will contribute degree 1 to this vertex and another degree 1 to this vertex. So each edge contributes 1 degree to, so any random edge. So this is one edge, suppose UV. So this edge, this particular edge will contribute 1 degree to U, another 1 degree to V. So it's very easy to consider this particular example. So this is one example, UV. Now, what is the degree of U? 1. What is the degree of V? 1. So this is very simple graph. And here you can see there is only one edge, but it contributes 1 degree to U, another degree to V. So every edge contributes 2 degrees. That's why summation of degrees would be 2 multiplied by number of edges, because every edge will contribute 2 degrees. That's why summation of degree would be 2 multiplied by number of edges. So it is always true. So we can write that this one contribute, this edge contributes 1 to the degree of U. Also, this edge contributes 1 to the degree of V. So summation of degree equals to 2 multiplied by number of edges. And the example that we take, handshaking example, it is also called handshaking theorem. Just think, one handshake to make for one handshaking you need 2%. The same concept is applicable here. Yeah, that's all, handshaking theorem. Any questions so far?
No, sir.
Okay, let's continue. Related to this, this is very important equation, very important. Related to this equation, there is another theorem exists that is called Euler's theorem. Euler is a scientist, very famous scientist. We'll come to know more about his problem. Euler's theorem is one very important theorem that you can directly get from this relation. So he said that any undirected graph has even number of odd degree. When you have to prove something, or when you want to prove something, or when you are confused, try to have some small example. Let's draw first. First draw and verify whether it is really applicable or not. That will help you to understand many concepts. And draw a very simple graph first. Like here, before getting to this proof, let's try to get one simple graph like this. And then try to grasp the concept. That will be very helpful always. So Euler's theorem is saying that any undirected graph has even number of odd degree. So that means you will have 0 number of odd degrees, or 2 or 4 or 6 or 8 and so on. So odd degrees means if there is a vertex with degree 3 or 1 or something, so suppose this is one vertex with degree 3, which is odd. So it is saying that the number of such vertex should be even. So it's not, it cannot be odd. So if this is one vertex U, this number of vertex, such vertex or vertices should be even. What do you think? Is it true or false?
I'm not sure about that.
Okay, so let's take one example. So it is an undirected graph, and this is a let's take an example of this graph. So this is one graph where the degree of this node is 2. This is the degree of this node is 3. Degree is 2, and for this node it is 3. So how many odd degree vertices are there? So this is one odd degree vertices. This is another odd degree vertices. And number of odd degree vertices is even. So for this particular graph, this is true. Let's take another graph. Okay, same thing. So what would be the proof? Let's see. V equals to V odd plus V even. What does that mean? Let's assume that in your graph, number of vertices is V. V is all set of vertices. So let's assume there are a couple of vertices with odd degrees, and there are a couple of vertices with even degrees. So we have assumed that. So this is all vertices, and this is vertices with even degrees, and this is vertices with, oh sorry, this is odd degrees, and this is even degrees. So we can assume that this set V is equals to V odd plus V even. So if we take summation in both sides, so it would be like this. Now, according to this formula, summation of degrees, actually this is actually degree, okay, summation of degree of all V. So degree, summation of degree. So we are trying to calculate the summation of all degrees. So what would be this value? Degree of all V. So it is nothing but this one, 2 multiplied by E. Now tell me whether it's an even term or odd term.
Even term.
Even term, because you are multiplying by 2. So it is an important conclusion. So summation of degrees would be always even, because you are multiplying E by 2. So whatever E is, it may be odd or even, it will always be this 2 multiplied by E will always be even. So summation of degree is always even. So this term is obviously even, summation of degrees of all vertices. And this term is also even because number of vertices is even. So this is also even. Now we don't know what is this one, whether it's a even or odd. So the question comes at this point is even equals to so what do you think? It can be odd or even. Like 4 equals to 2. It can be it. Is it possible that this term will be odd? Is it possible that odd plus even equals to even? Is it possible ever?
No.
No. So this term is obviously even. So this is Euler's theorem, which is saying that any undirected graph has even number of odd degrees, which is actually same, coming from this equation, handshaking theorem. Okay. So, although I prefer 1 hour class, but it's because of short time and lots of things that we need to cover, I need to this duration might be more than 1 hour. So you are free to leave if you want. It's up to you, and based on your time permits. I will continue this topic maybe for another 1 hour. So we'll do a couple of simple exercise so to grasp the concept. So the first question one is, this is one graph. A, B, C, D, E. And first thing that you need to find is find number of vertices, number of edges, and degree of each vertex. Let's do this for this particular graph. So number of vertices. So how many number of vertices? How many vertices are there? A,
5.
B, C, D, E. 5. Yeah. And number of edges would be A, B, B, C, 2, 3, 4, 5, 6. And degree. So degree of A equals to 2. So degree of A is 2. Degree of B equals to 1, 2, 3, 4. Degree of C equals to 1. Degree of D equals to 1, 2, 3. And degree of E equals to 2. Even you can see in based on previous proof, see there are only 2 even number of vertices with odd degree. So this is also applicable in for this example. Also, yeah, the second part I also discussed that find the sum of the degrees and verify it equals twice the number of edges in the graph. So summation of degrees equals to 2 plus 4 plus 1 plus 3 plus 2, which is 6, 7, 10, 12, which is equals to 2 multiplied by number of edges. A number of edges is 6. So 2 multiplied by 16. So it verifies that it equals twice the number of edges. Very easy problem. Now, yeah, it is some interesting, slightly tricky question. Can a simple graph exist with 15 vertices, each of degree 5? What do you think? Is it possible? Can a simple graph exist with Number of vertices is 15, each of degree 5. Is it possible at all?
No, because 15 is an odd number.
Which is odd number?
15 vertices.
No, one graph might have odd number of vertices. That's fine. Like this graph. This graph has 3 vertices. That's fine.
Oh, maybe
You
I'm
are
just.
on the right track.
Is it the opposite of what
So-
I'm saying? That the degree is opposite. So
Yeah,
it's
right.
not divisible by 2.
Degree, the summation of all degrees would be 15 multiplied by 5. That is 75, which is odd number. Yeah, you are right. So it's not possible because we have understood from this relation that degree is 2 multiplied by number of edges. So it is always an even term. It cannot be an odd term. So here in this case, we have got odd terms. So it's not possible. So we cannot have a simple graph with 15 vertices, each of degree 5. It's not possible. This is very important for your final exam. Okay, now this is another very interesting, same based on the whatever you have studied so far. Let G be a graph with V vertices and E edges. So these are the number of vertices and number of edges. Let M be the maximum degree of the vertices of G and small m be the minimum degree of the vertices of G. Now you need to show that 2E by V is greater equals to M and 2E by V is less than equals to M. What do you think? Hints, let me give you one hint. Hint is same handshaking theorem, degree of all vertices equals to 2E. Here, in this case, 2 small e. Number of edges is small e. And degree of all vertices, VI. What do you think? Okay, let's first calculate what is the total summation of total summation of degree of all vertices. It is 2E, right? From this equation. So 2E is the summation of all vertices. So obviously the question would be, what is the average degree? 2 is the total divided by number of vertices. If you divide 2E by number of vertices, then you will get average degrees. So it is nothing but a 2E by V, because V is number of vertices. So we got this term 2E by V. It is average vertices, average degrees. Now it is given that capital M is the maximum degree and small m is the minimum degree. So obviously this is average degree. So average degree should be greater than the minimum degree and obviously is less than maximum degree. So M is the maximum degree which is given and small m is the minimum degree which is also given. So obviously average degree should be greater equals to minimum degree, less than equals to maximum degree. So we have already proved that this is nothing but, see, average degree should be greater equals to smallest degree and average degree should be less than equals to maximum degree. So we have proved that. So same handshaking theorem, we can prove this thing. So this is also important for your final exam. Okay, let's continue our discussion. Okay, now since you are most probably for the first time you are introduced with the graph, so you have to study a couple of different kinds of graph along with some different terminologies which you have studied for the first time. So in the beginning you have to memorize or you have to take notes of different kinds of graph or different terminologies, like what is vertices, what is edges, what is degree. This type of terminology, graph terminology, most likely you have introduced for the first time. You are introduced. So we'll discuss some special simple undirected graph. Special simple undirected graph. Number one is very important, is complete graph. So what is complete graph? It is very important actually. Complete graph. Complete graph is, tell me what is the difference between these two graphs. Suppose this graph is G, this graph is H. What is the difference between these two graphs? Here you can see that this graph G doesn't contain all edges, means this edge and this edge are missing. Means this node and this node, there is no edge. There is no edge between these two nodes. But in graph H, you can see there is an edge in between every pair of vertices. So when there is an edge between every pair of vertices, then we'll call it complete graph. So the term you may think complete means there is an edge between every pair of vertices in that graph. So this is an example of complete graph, but G is not an example of complete graph. So exactly one edge between every pair of vertices. And it is denoted as K, capital K suffix N. N is the number of vertices. So this graph is nothing but a K suffix 4 because number of vertices is 4. So if I say K3, how do you do that? K3 is this one. What is K2? K2 is nothing but this one. What is K1? K1 is just only vertex, no edge. And this is K4. What about K5? K5 is this way. So 1, 2, 3, 4, 5 vertices, and there is an edge between every pair of vertices. So this is K5. In this way, you can draw K6, K7, and so on. So this is very important, complete graph. In later semester, you might take data structure course where you will study complete graph or heap sort, some sorting technique. These are very important for your job interview as well. So complete graph is very important. You will study why complete graph is important at that time. I'm not going into that details, but if you have taken data structure course or algorithm course, then that importance should be clear to you. So this is complete graph, means simple. There should be an edge between every pair of vertices in that graph. Okay, let's move on. Next is cycle graph. So graph that contains cycle, it is denoted as C suffix n. So C3 can be like this. So C3 is a cycle graph containing 3 vertices, 3 edges. So in cycle graph, number of vertices equals to number of edges. So this is C3. So you may think C2. In C2, it's not possible to have any graph. So C2 doesn't exist. Similarly, C1 doesn't exist. So C3 is the first graph or cycle graph with minimum number of vertices. You may think C4. So this is C4. So there exists a cycle and number of vertices equals to number of edges. Similarly, this is C5. This is C6. So this is cycle graph, which is called wheel, which is denoted as W suffix N. So wheel is nothing but So wheel is nothing but very similar to cycle graph, but there is another vertex will be added. So number of vertices in wheel would be 1 plus number of vertices in cycle. So this is one cycle graph. So if I want to make it wheel, so there will be one edge and that one vertex, and that vertex will be connected to every other vertices. So it will become a wheel. Another would be, suppose this is your cycle graph. So there would be a vertex, and that vertex will be connected to every other vertices. Now it becomes a wheel. So additional So this way you can get wheel graph. Okay. Now another fourth graph is very important. It's called bipartite graph. It's very important. Okay, let's try to understand what is bipartite graph. Let's assume, let me take a couple of your name like William. Okay, William. So here I will write person name, and here I write the movie name, which that person likes most. So William likes maybe the Jungle Book. I'm randomly writing Jungle Book, the Spider-Man, maybe Aditya, maybe he likes maybe a beautiful mind, only this one, and maybe Henry likes the Spider-Man. Also maybe inception. And another student maybe likes maybe Lord of the Rings. Or Saving a Private Ryan. So here I have listed a couple of person and their choice of movie list. So how you can represent it using a graph. So you may think this is William, this is Aditya, this is Henry, this is Kyla. There are 4 vertices. And also each book can be represented as a vertex. So this is Jungle Book. This is Spider-Man. This is Beautiful Mind. This is Inception. This is Lord of Rings. This is Saving a Private Ryan. And did I miss anything? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Yeah, we are done. So William likes Jungle Book. William also likes the Spider-Man. Where is Spider-Man? Yeah. Aditya likes A Beautiful Mind. Henry likes Spider-Man. Henry also likes Inception. Kerala likes Lord of the Rings and also like Saving a Private Ryan. So this is one graph, you may think. So in this graph, the vertices are William, Aditya, Henry. These are vertices. Also, this movie name is also vertices. Now see a couple of interesting facts. So this is a set of vertices. Suppose, let's assume it's V1 and this is V2. So V1, every member of V1 likes some movies in V2. So if you choose any random edge, so let's assume this is one edge. Choose any random edge. One end of that edge will belong to V1 and another end of this edge will belong to V2. And at the same time, this is one observation. Another observation is there is no edge between 2 members of V1. So there is no edge between 2 members. See, there is no edge. At the same time, there is no edge between these 2 members of V2. And no edge. It means it makes sense because William likes movies, not William likes Aditya or William likes Henry. Here we represent person who likes some movie names. So there should not be any edge between 2 nodes of same set for this particular example. Similarly, Jungle Book should not like some other movies. So there should not be any edge between 2 movies in V2. So this is one kind of graph where each member of V1 might connect it to some member of V2, but it's not possible that 2 members in V1 will have some connection or 2 members in V2 will have some connection. So this is an example of bipartite graph. Bipartite graph. So what it is saying, bipartite graph, suppose the number of vertices is V, so set of vertices is V, you can divide the vertices into V1 and V2 like this, V1 and V2, such that there should be an edge between from V1 to V2, but no edge in between two members of V1 or no edge in between two members of V2. So this is a kind of bipartite graph. Why it is important? It has a large application. One application you may think like this way. We can take another example. Like you are welcome to provide your favorite teacher name at AUM or in your previous school days. Let's assume one teacher name is, I don't know, X, Y, Z. These are a couple of faculty names. Okay, faculty members' name. And each faculty member teaches some subjects. So X may teach, subject A, subject B, Y may be teaching C, D, Z may be wants to teach E. So X wants to teach A and B, Y wants to teach maybe B and C, Z wants to teach D or C or E. Now, just think you are the department chair. So you need to assign each course to a particular faculty, right? It's not possible that this faculty will teach this faculty. Faculty will teach a subject or course. So there should not be any edge between two faculty members. But there should be one edge from one faculty to some subject or courses. So this is an example of bipartite graph. So job scheduling is one area. If you have taken operating system course, so job scheduling is one area where bipartite graph has major application, in addition to many other applications too. So let's briefly discuss bipartite graph. I hope you have got the basic concept of bipartite graph and the importance. So simple graph G equals to VE is bipartite if there exist subsets V1 and V2 such that V1 union V2 equals to V and V1. Okay, this is concept of set. I hope you have you can understood this. And for each edge, one end belongs to V1 and another end belongs to V2. Okay, what it is saying, a graph G is bipartite if there exists subsets V1 and V2. You may think this is your set V, and there you may divide V into two parts. One is V1, another one is V2. So you can divide this like this way. And what does that mean? V1, you may consider union as addition. So when you add V1, set V1, all member of V1 and all member of V2, if you add them, then you will get the whole vertices, number, all vertices. And if you intersect means, is there any common? So if you see, is there any member in V1 and V2, is there any common? Or if they intersect? So no member of V1 is a member of V2, right? So no member of V1 is a member of V2, as well as vice versa. So no member of V2 is a member of V1. And for each edge, one end belongs to V1, like choose any edge. One end belongs to V1, another end belongs to V2. That's bipartite graph. So let's take a couple of examples like A, B, C, D. Is it a bipartite graph? So if you think AC, and if you take BD, we are representing the same graph like this way. Now, AB is one edge, AC, there is no edge, AD, another edge. In this figure, BC is one edge. There is no edge between B and D, and BA is one another edge. BA is already there. Okay, and DC is another edge. So see, there is no edge between two members of this set V1, and there is no edge between two members of this set V2. And all edges, choose any edge, one end belongs to V1, another end belongs to V2. So this is a bipartite graph. And what this graph is, this is actually C4, means cycle graph. See this one, C4. So this is C4. So C4 is a bipartite graph. Okay, let's see another one. This is a complete graph, K4. Is it possible that K4 is a bipartite? The answer is no, it's not possible, because every member, there is an edge between every two pair of vertices. So there is an edge between A and C, there is an edge between B and D. So you cannot divide the vertices into two parts, so that each member of V1, there should not be any edge. But in this case, there will be always one edge between every pair of vertices. So K4 is not bipartite. We can take another example, like this. I don't know whether it's a bipartite or not. If we think A, C, if you choose A, C, you cannot choose D, because D is connected to C. So you cannot choose D. You cannot choose E either, because D and E are A and E are connected. You cannot choose B, because A and B is connected, or B and C is connected. So you can choose AC in one set, but in other set, you can choose, okay, B, you can choose D, but can you choose E? No, because D and E are connected. So it's not possible to divide the vertices into two subsets here. So this is not a bipartite either. Okay. So similar to bipartite graph, there is also some graph called complete bipartite graph. Which is denoted as capital K M, N. So same complete. Complete means there should be all edges. So here complete graph means, suppose this is one graph. Now the edge looks like this way. And there is another graph very similar to the previous one. Okay, this is graph G, this is graph H. Now, what is the difference? Can you find any difference between G and H? If you think closely, see, there are many edges which are not there at G, like this edge. There can be a valid edge, but it is not there, like this edge, like this edge. These are valid edge, but it is not there. So in case of complete bipartite graph, there will be all edges should be present there, which doesn't violate the bipartite property. So all edges in this graph, you can see all edges are there, all edges. So this is complete binary, complete bipartite graph, and it is denoted as K m comma n. Means m is the number of vertices in this set, n is the number of vertices in this set. So for this particular example, K number of vertices 2, 3. So this is complete binary, complete bipartite graph with 2 vertices in one set, 3 vertices is another set. So K 2, 3. So we can draw a couple of other graphs like K 3, 3. 3, 3 means one set will contain 3 vertices, another will also contain 3 vertices. And since this is complete bipartite graph, so all vertices of this set will be connected with all vertices of that other set. So this is K 3, 3. Also, you can draw K 2, 6. Means in one side you have only 2 vertices, in another side you will have 6, 4, 5, and 6. So 6 vertices, and every one will be connected to every other vertices in another set. So this is one complete bipartite graph. And again, please note that there should not be any edge. So this is one subset. There should not be any edge between 2 members of a same set. There should not be any edge. There should not be any edge. There should not be any edge. All edges should be like this way, where one end would be in set V1, in another end would be in set V2, like this. So if you consider the example of Part1 and their choice of movies, then you can easily understand the concept that Part1 will like one movie. It's not that one person will like another person. Okay. Okay, next we'll talk about, we have studied many graphs. We have studied many graphs like complete graph, cycle graph, wheel graph, bipartite graph, complete bipartite graph. Next, we'll talk about representing graphs. Means when you do programmatically, how to represent a graph programmatically. It's okay, I have understood graph contains set of vertices, set of edges, but how to programmatically we can implement a graph, that we need to know. Basic thing, very easy, it's not difficult. So one way is adjacency list. Another way is adjacency matrix. And another one is incidence matrix. Out of these 3, we'll mostly focus on these 2. This is very important. And you will need this when you will study data structure algorithm course. You need to know this too at that time. So how you can represent any graph using adjacency list, using adjacency matrix. We can choose any either one is fine when you do programmatically. So let's take one example. So this is one graph. A, B, C, D, E. So this graph contains 5 vertices and 1, 2, 3, 4, 5, 6 edges. Now, how we can represent this using adjacency list? So first we'll do adjacency list representation. How we can do? So the list will look like vertex and adjacent. Very easy, actually. adjacent vertices of that vertex. So vertex are A, B, C, D, E. And now what are the vertices which are adjacent to A or neighbor of A, means who are directly connected to that vertex. So who are directly connected to vertex A? So A is directly connected to B, A is directly connected to C, A is directly connected to E. So it would be B, C, E. Now, what about B? Who are neighbors of B? The neighbor of B is only A, because B is only connected to A. What about neighbors of C? C is connected to A, E, D. A, E, D. Now D. D is connected to C as well as E. C, E. And E is connected to A, C, D. A, C, D. So this way we can represent a graph. And adjacency list, I don't know whether you have studied data structure course or not, then it is implemented using linked list. Linked list is pretty similar to array. I think you have studied array before. So using linked list, you can easily implement this graph. So this way we can represent a graph. So same thing, whatever we have drawn here is reflected in this using this adjacency list representation. Very easy. So vertex and corresponding adjacent vertices. Adjacent vertices means neighbor vertices. Using adjacency list we have seen. Similarly, using adjacency matrix, we can also represent the same graph. So let's do the same thing using adjacency matrix. So it's a matrix. So, okay, this is matrix. So here you need to put all vertices A, B, C, D, E, and A, B, C, D, E. Now each cell, each value represent whether there is an edge between two vertices or not. So A to A, there is no edge. So it would be 0. A to B, there is an edge. So 1. A to C, there is an edge 1. A to D, there is no edge. So 0. A to E, there is an edge. So 1. B to A, there is an edge. B to B, no edge. B to C, no edge. B to D, no edge. B to E, no edge. C to A, there is an edge. C to B, no edge. And C to A, B, C, no edge. C to D, there is an edge. C to E, there is an edge. D to A, no edge. D to B, no edge. D to C, 1 edge. D to D, no edge. D to E, there is an edge. And E to A, there is an edge. E to B, no edge. E to C, there is an edge. E to D, there is an edge. E to E, no edge. So this is another way to represent a graph. So what we are, why it is important? See, we are only tracking edges. We are only tracking edges, whether there exists an edge between a pair of vertices or not. Both of these representation are trying to track that information. That's all. So this is the way to represent adjacency matrix, and this is the way to represent the graph using adjacency list. Which one you will prefer? You can choose either one, or you can choose, most of the cases we will choose adjacency list. But in this discrete math course, we don't need to do into that depth. You will do that when you will take data structure or algorithm course. Why adjacency list is preferable? Because when your graph contains less number of edges, so now how many entries are there in this one? B, C, E, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And how many information are here? It would be 5 cross 5, that is 25. So the whole thing you need to save into your memory when you do programmatically. So 25 units of memory will be saved. And here only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 units of memory that needs to be saved. So it will save some memory. So when your graph is sparse, then you will use adjacency list. And when the graph is dense, means lots of edges, many number of edges are there, like complete graph, then you will use adjacency matrix. But both are fine to use. Both are very efficient. Okay, then. So let's take one example. This is one graph which is given. Now you need to find its adjacency matrix. How to do that? Just draw the matrix first, A, B, C, D, A, B, C, D. And see, A to A, there is no edge. A to B, there is an edge. A to C, there is an edge. A to D, no edge. B to A, there is an edge. B to B, no edge. B to C, no edge. B to D, there is an edge. C to A, there is an edge. C to B, there is no edge. C to C, no edge. C to D, there is an edge. D to A, no edge. D to B, there is an edge. D to C, there is an edge. D to D, no edge. So this is the corresponding adjacency matrix for this particular graph. Yeah, that's all. Okay, I understand it's a lots of material that I am providing, but again, we only have around 1 month. So my plan is to go through graph and then followed by basic introduction of tree. So graph, tree, as well as we'll cover set, relation, and function. I think that would be more than enough considering this time limitation. And again, feel free to let me know if you have any doubt, any questions, or if you think that it's too much or whatever you think. Again, my goal is your success. So whatever steps that I need to take to make you succeed, I will take that steps. So feel free to reach out to me whenever, whatever you think is beneficial for you to make yourself succeed. So the recording is there, and I'll try to share the notes that I have taken throughout this lecture period, and I will upload that too. And let me know whether you prefer live session. If so, what time do you prefer? I might, if I am available, I'll try to I'll try to have that live session at that time, so that many students or majority of the students can attend that session. And that's all. And feel free to let me know your feedback. That's all. So having said that, I will frequently try to post videos so that you can you will be on track, and try to grasp the concept of graph. That's very important for this course, as well as multiple future courses like data structure, algorithm, networking, and it would be also very important for your job interview. Yes.
Just checking, you said graph, tree, set, and relation is going to be the scope of the next month?
Yes, set, relation, and function.
Function, that's the one I missed.
Yes.
Okay. And these concepts are the only thing that's going to be on the final?
Yes. Whatever
Okay.
I will cover, that will be in your final exam.
Okay, that's great to know. I'll try to be at these when I can. I'd rather be here live so I can ask questions.
Yeah,
But I
feel free
appreciate.
to ask. Yeah, go ahead.
I'm sorry. I appreciate you stepping in and taking the time and doing this for us.
Yeah, that's yeah. I actually Dr. Ru requested me, and I am always I want to do my best for my students. So if I can help any students in any way, I'd be glad. And I would also thank Ms. Donna Jackson and Dr. Wu for giving me this opportunity. And I wish I can meet you in person. That then the class would be more interactive, more interesting. But even though we are meeting over Zoom, and feel free to reach out to me and talk to your friend so that we can arrange a time when we can meet over Zoom and majority of the students can attend that class.
I just have one suggestion.
Yes.
So could you do the live sessions on Saturdays and Sundays, because some of the students have classes during Monday to Friday, if possible, I mean, because I really want to attend these live sessions.
I understand. Saturday, Sunday, I can't commit, but I will try. First, let's one thing you can do by yourself, go to Doodle and try to create some session and reach out to your friends and see whether there is a common time where we can meet during weekdays, or I can create that Doodle. So that if you see that there is some time when in weekdays we can meet, then that would be the first priority. Because on weekend, I can't guarantee you that that would be the schedule, or I can request other students to attend that session.
Trying to live my life, hang out with my baby.
Sorry?
I'm trying to live my life on the week. I'm trying to live my life on the weekend, hang out with my kid. Sorry. I couldn't do the weekends. That's family time.
Yeah, let's prioritize weekdays, and if not, then let's see. First, Aditya, I would request you. Are you familiar with Doodle?
Yes, sir.
Yeah, just go to doodle.com and you can create a schedule and just share the link with me so that I can let you know my availability. And let's see if there we can get some time, including Saturday, Sunday, so that we can meet in this live session, and we can continue our lecture and discussion as well.
Okay, sir. Got it.
Okay. So I'll upload the recorded lecture, and again, feel free to let me know what is your feedback so that I can change, because this online teaching is totally new to me. So until you provide me your feedback, I might repeat my mistakes. So feel free to reach out to me so that that is most beneficial for you. Okay.
Cool. I might come say hi to you in person at your office one day, just to say hi.
Yeah, sure. Feel free to stop by at 309L. I'm mostly available on Tuesday and Thursday in office, and on Wednesday I mostly work remotely, so I'm not sure. But again, feel free to stop by on Tuesday and Thursday.
Cool. Well, have a great rest of your week. Thanks.
Yep.
Thanks again.
Thank you so much for attending this session.
Thank you, sir.
Thank you. Bye. And
Bye.
have a great rest of the week.
You too.